Hello, I'm Blagoje and welcome back to my channel. In this video I would like to talk about the logic behind ESP32 Macropad that I would like to create. I saw a couple of versions of Macropad or mini keyboards online, but everyone were missing something that I would like to implement here and that I would like to talk about later. Also, not all of them are based around 32 microcontroller, and maybe by adding this controller, this gives us opportunity to have some kind of web server running on it. And with that web server, we can maybe on the go configure our macro keys. By doing so, we eliminate possibility of running this board wirelessly, because in that case ESP32 will draw a lot of current, but at least we have possibility to do something like this. But let's dive in a bit deeper into logic behind this macropad and how I would like to do things. So first thing first, I will need to have some PCB layout, which I am designing right here now, and I'm thinking of maybe adding additional column here, so that we have 5 times 3 keys, and I think all of those keys can be serviced by ESP32 without any need to create some kind of matrix. Furthermore, in parallel to this, I would like to start on designing the software for this, and for that reason I created this demo that is basically just 2 switches connected to ESP directly and created simply copy-paste functionality. So I would like to explain how I did this, and then how can I create full macropad. So I'm basing around this macropad around ESP32-S2 microcontroller, and we need S2 or S3 version of this, because in those microcontrollers we have integrated HID or human interface device functionality. So our PC can detect this device as USB, keyboard or a mouse. Next, I would like to talk about logic behind mechanical switches, because we would like to use this. So in every video we just see basically something like this. So simple connection from the switch that is represented here as switch push. It is connected to the ground, and the other pin is connected to the input of microcontroller. But this is simply not good enough, and something else is happening in the background. So with this, for example, if you can imagine, if we have button pressed, ground will be short to our digital input and everything would be fine. We would read that our digital ESP32 input pin is pushed to ground. But in the case when the switch is opened or unpressed, we have a floating line here. Because of this, we all the time need to add this pull-up resistor in order to fix this floating point. So now when our switch is pressed, we will read as well 0 at digital input pin, but in case when switch is open with this via this pull-up, we will have a VCC applied to our input pin, and in this case we would have 3.3 volts readout. And now we are coming to point that I would like to make with this video. I'm not saying that this is right or wrong, but I'm saying that I didn't see anything like this on internet, and basically if we are creating custom PCB and custom layout for our keyboard or macropad, and if we are using a small amount of keys, maybe it's a good thing to implement some kind of debouncing in the hardware. In existing projects, the debouncing is mostly done inside the software. So But what is debouncing? Debouncing is basically a feature of mechanical switches that they cannot instantly change position. So if you see basically this image here, we can see what it means. So when we have our switch open and we would like to close it, we will drop from VCC to 0 volts. But in between we have these short bounces, and this is not good for us because in this point we can detect multiple clicks, and or we should delay our acknowledgement of the key press in order to clean this. So usually, in order to fix this behavior, we are doing something that is called debouncing. Debouncing in the software is pretty easy now with the speed of microcontrollers, but maybe if we are already creating some kind of PCB, we can maybe include some debouncing circuit inside PCB directly. The simplest way to do this is basically just adding one active component inside our circuit, and that's capacitor. This is very good because the capacitor cannot change its voltage instantaneously, but it changes over time. So we will have something like this on switch opening. When our switch is closed, we will have here short to ground, and our C1 capacitor will drain itself, and it will have 0 volts on it. So the readout from digital input from ESP32 will be 0. Then when we have open our pull-up switch in this, I will show this now by removing this part, we will have something like this. So we will actually charge C1 via R1 resistor, and we will get some curve like this. We can modify the slope of this curve by increasing or decreasing R1 and 1 resistors and C1 capacitance. So we can make this curve much faster or much slower, and with that control our debouncing. But the problem with this approach is now, for example, if you can imagine that we would now like to discharge our C1, or in other words, just press our switch. When our switch is pressed, that's what I represent with this now, we will have a circuit like this. So basically it means that we would discharge C1 to the ground via this short circuit. This is exactly not short circuit. We have some resistance here from a closed switch itself, but it's very small. So if we now see, we are basically then charging our C1 via R1, but discharging with the other resistors. So we don't have equal charging and discharging. So this can be improved, and we are discharging here via almost short circuit, which is maybe not so good solution. So if we take a look at something different here, we add here R2 in between. So this is helpful a bit, but then again we have mismatch via discharging and charging. If we would like to see the charging of C1, it would be something like this. So we are now charging by a constant that is basically equal to R1 plus R2 times C1. So not bad. But we are decreasing the charging time. And when we are discharging C1, now we are discharging only via R2. So this is again not ideal, but we have somehow control over discharging via R2, but again charge and discharge time are not the same which we are searching for. Then maybe we have the best solution here is by adding this diode. that will basically influence that when charging we are actually skipping this resistance R6. Maybe for explanation purposes I will just change this to R1 and R2 as well. So, and this to C1. So, if we now take a look how we are charging, and if we take the general purpose diode, which is as close as possible to ideal diode, we can see that our state here is next. So when we are charging this switch is open, so we have this line. Our diode is conducting current, so we can remove this as well. So we will charge C1 only via resistor R1. But if we in the other case have this switch closed, so if we have this switch closed, this diode won't lead any current, so we can remove this. And because this is short to ground, it doesn't have point to notice this R1, so we would discharge via R2. And if now R1 and R2 has the same resistance, we are fine. Let me go back to my original circuit, and because of this we can see something like this. So when we are closing our switch, we have here debouncing, but in our output to our microcontroller we have some decreasing slope like this, and equal increasing slope when we are charging via R1. Of course, by modifying these constants we can decrease this sloping time and this rising time here, but then we are becoming more susceptible for rising and falling here. So if we would like to have this smooth time, we have something like this. But now we have a problem. We cannot react as fast to our switch. So basically we will react only here and here from our switch press, and that can take some time. So if we have action here and we can only detect that our switch is closed here, and this time is multiple milliseconds, this is not okay. But how can we fix this? It is simple. We can add simple inverter with Schmidt Trigger. What Schmidt Trigger basically does is as inverter, just with different thresholds from when it's going from high to low, and different threshold when it's going from low to high, and that can be explained in the image here. So we have basically the same wave here with decreasing and increasing, but now we have multiple levels of when we are achieving when we are detecting logical high and logical low. So we have 1 and 2 level in our hysteresis. So when we are going from high to low, we would detect, we would trigger on this line the change, and when we are going from low to high, we are using this line. And with this, you can see that we are actually increasing the time when we detect the change. So we are detecting the change by this time faster. I know that this is maybe now too complex, and that will increase the cost of your board, but I didn't see that anyone else is doing some harder debouncing for the macropad, and I decided to try this. This will maybe be stupid because our microcontrollers became much faster, so they can process this and the other functionality, but let's try maybe outsourcing the bouncing to the hardware. I think that with small components and good PCB design, I can place basically below each keycap a corresponding component, maybe not going for the full setup like here, but maybe going for some solution like this. Furthermore, I forget to mention this. Why we don't usually see this setup, and this is needed because usually this R1 is integrated inside the GPIO, and when you are configuring your GPIO as digital input, you can add that it should be connected to internal pull-up. So we can basically outsource this part to our embedded controller. But because of the logic sake and transparency, I'm leaving this as is. So if I would like to have some kind of hardware debouncing, at least I would need to add one capacitor in parallel to my switch, or maybe just add capacitor, resistance and diode, and in the far more difficult case, I need to add one inverter with Schmidt Trigger as well. So in the next video, I will try to incorporate this into one small DIY pad, and let's see what happens. So see you in the next one.